All right, let's look at the first couple real quick just to make sure everybody's on the right track. And is everybody cool with the fact that, I think I've said this before, but what's 0 factorial? It's defined to be 1. So it doesn't matter that it starts at 0, it's okay. It's a good thing to check though. So what's Cn? 1 over n factorial. Cool. Just, again, that doesn't help you in any way really. You just want to make sure you can identify the parts of this. How do I set up this ratio test?
X to the n plus 1 over n plus 1 factorial times n factorial over x to the n.
Yeah, so it's just that guy flipped over here, and then that guy with an n plus 1 in it there. Right. It's always the next term divided by the previous term. So technically you could make it n and n minus 1, but don't. It would still work, but just don't. So what happens here? Here,
You get an x.
yeah, n x's canceled, you get 1 left up there. And of course here, I can rewrite n plus 1 factorial as,
X plus 1 times factorial.
well, you just stop when you match this guy. So now he's gone. So what is this limit then?
0.
Hold on, not, wait. So I get the limit, n goes to infinity,
X over n plus 1.
x over n plus 1. And don't let x freak you out. X is a constant. We just don't know yet what I'm allowed to plug in. So whatever the hell somebody plugged in, it's a constant. It could be a really large constant. But n plus 1 doesn't give a shit because it's going to freaking infinity. So it says, however big you make your constant, I'm going to pass it by at some point. Right? So this thing definitely goes to 0, which is less than 1, always. So just like in algebra, I think a lot of you guys heard me say this. When the x goes away and you end up with a true statement, the answer is all real numbers. It's the same thing. So the x went away. The resulting statement is true, always. So the interval of convergence is negative infinity to infinity. The radius is infinity. I don't like that expression, so we can say infinite radius. All right, how do we feel about that so far? So that's one case. One case could be everything works because the bottom was enough to handle the top no matter what. You can kind of see that from the beginning. N factorial is going to grow really damn quick. Quicker than the top would. So that kind of makes sense, the answer coming out. How do we feel about that? Is that all right?
Yeah.
You guys look weird kind of mix of emotions. All right. So what about number 2? So here, obviously there's no endpoints to check, right? I can't plug infinity in. So that's the one time you don't have to worry about endpoints. The only time you have to worry about endpoints is if you get a conditional expression. If it goes to 0 or infinity, you're golden. So what about number 2? Oh, sorry, 0. So what's Cn? Square root of n, cool. So that's Cn. How do I set up this ratio test?
Square root of n plus 1 over square root of n times.
And whenever it's just a straight line deal, you can just go, just put the other guy in the bottom like he's supposed to be. So over square root of n, x to the n. Have you picked up on what's almost always going to happen? You're always going to lose n x's, pretty much always. All right, so I lose n x's, so I got an x left up top. And then what's this limit here?
1.
Yes, 1. Cool. So the limit comes out to be absolute value of x, and in order to converge, that has to be less than 1. So again, what we really see here is, even though I've multiplied by root n, as long as that is less than 1, it's still a convergent geometric kind of series, right? Cool. Okay. So that's pretty much what this is. So what's the last piece I got to do here? Check the endpoints. The big mistake I see here is people plug that in to n. But of course, these are values for x, right? So what do I get if x is -1? I get this series, square root of n, -1 to the n. It's alternating, but this limit is infinity, right? So I don't care that it's alternating, it's still going to diverge. How we do there? Okay. So it's going to be this weird oscillating divergence, right? But I don't care, it's divergence. So I don't want to include, that's fine the way it is. What if x is 1? And it's even a little worse or a little better depending on how you feel. So it's going to be the sum of root n. So root 1 plus root 2 plus root 3. That's going to definitely diverge. So that's fine. So that's my interval of convergence. And of course my radius would be 1. Right? The diameter is 2 from -1 to 1. So the radius must be half that. Okay, all right. You guys are controlling your motions. Yes?
The balance have to be divergent.
Do one more time.
The balance have to be divergent.
They don't have to be, no. In fact, we did one a minute ago where one side was fine and the other side didn't work. So they could either both work, they could both not work, or one of them could work. That's why you have to test both of them. Cool. Have you guys tried the third one out yet? Try the third one out. We'll do it. No. You don't want it. There's no need. The ratio exactly is awesome. This whole thing with n plus 1s and you're taking the absolute value, so don't forget you can kill that -1 at the end. You've already done that, so don't forget your absolute value. So there's no need. And you really got to work. You can't take the limits of two pieces separately.
Okay.
Because you could end up in an indeterminate form and actually the limit of 1 over x times the limit of x. That would be 0 times infinity. When really, if you just put them together, it's the freaking limit of 1.
Yeah.
Good. Don't forget your absolute values.
Oh yeah, yeah.
That's what leads you there. I like it. And then you check the endpoints.
Yeah, I did. I kept getting. I checked my negative endpoint, and then I checked. Yeah, I did. That's what this is up here. I got a 0, and then.
Now be careful. It's not just, you got to look at the series to see if it converges. So if you put a 3 in, you'll end up with -1 over n plus 1.
Right, which will converge to 0.
Which converges because it's alternating series. It doesn't converge.
Well, the
Zero.
series, the
series
sequence goes to
converge.
0.
The sequence,
yeah,
which means the series might converge. So you got to be, but when I plug a -3 in, something very interesting happens. So -3 should actually not be included. Yeah. Oh, so this one would be for alternating series, what's got to be true? It's got to be decreasing. Well, it's not. The limit's got to be 0. So divergent. So it would just be -√0 plus √1 minus √2 plus √3. It would just keep bouncing back and forth to infinity, -2. And then this one's even more direct. Now I'm adding the square root of n forever. Square root of 0 plus square root of 1 plus square root of 2 plus square root of 3. It's going to get bigger and bigger. It's going to go to infinity. Yeah. Cool. And the test for divergence would show you the limit's not 0. So it doesn't have a chance to diverge. Oh, you switch those. It's always got to be n plus 1 stuff first. Oh, and when your x is in the bottom, that gets really weird. You don't want that to happen. So Cn is rather large this time, right? It's everything that's not x minus a to the n. So all this business here. When you set this up, you can kill that part, of course, because you're taking absolute values. So anytime you're alternating, just don't write the -1 to the n. Don't freak out about that. It's just gone. The absolute value kills it. All right. There's my n plus 1th term. There's my nth term. So what happens here? I lose... Yeah, I lose nx's again. I lose n3's. Let's see. So far we've got x over 3. And what's the limit of this here? Good.
So any values of x over 3.
So this limit is x over 3. What's got to be true for it to converge? It's got to be less than 1. Therefore, absolute value of x has got to be less than 3. See, that's what I was saying about earlier. Since x is not by itself yet, multiply the 3. Now you know the radius is 3. Because x is by itself, right? And of course, I can write that as -3. Cool. And of course, the last thing I got to do is check it. And this gets interesting. And you're all like, well, every damn thing is interesting here. I don't think you choose that word, but let's see. So if I check, let's check 3 first. That's the one that's not quite as freaky. So my original expression looked like this. So if x were 3, if I allow x to be 3 and plug that in, I end up with -1 to the n, 3 to the n over 3 to the n, n plus 1. So of course what immediately happens?
3's go away.
The 3 n's go away, 3 to the n. I end up with a series that by itself would diverge, but because it's alternating, it's going to converge because the limit of 1 over n plus 1 is 0. So that it meets the requirements for alternating series. So that's going to converge. So what can I change? Do I change anything up here? I want to include 3 in my answer, right? Because 3 allows it to converge. So my interval is always the values that let the series converge. So this gives me the inside values, and then I just got to check the guys on the outside. So I can include 3 because it makes it an alternating convergent series. Now -3 gets a little weird. So if I plug in a -3, if x were -3, I get the sum. I write even worse that way. All right. -3 to the n over 3 to the n. Now be careful. Can I just cross those out?
No.
Did I leave anybody else? No, we got to. So how do you take care of this then? What the hell? What the hell, man? I can rewrite -3 to the n. What is -3? It's -1 times 3. So I can, once you see this, you see it's going to happen a few times. We stop right there. Is that cool? I distribute the n to the 3 and to the -1 that's inside, right?
Yeah.
So I can pull that oscillating piece out. And what happens to the 2 oscillating pieces? They cancel. Right? When n is 1, they're both negative. When n is 2, they're both positive. So at every step, they both become 1. So they effectively kill each other. And of course, what else dies? 3 to the n. And I'm left with that which diverges. So I don't want to include -3. Done. So once you see that, you realize you're allowed to do that, because you can see that's going to happen decently often on these problems, where you have a negative inside of an nth power. You just pull that -1 to the n out, and then it can kill anything else that's there. Right? All right, so what about this last guy? Let's do this last guy. All right, so Cn,
1 over
1 over n squared. And one reason you sort of want to look at Cn is it very often is going to be involved in the answer. That if that was there, it would just be a convergent p-series by itself, right? So I kind of keep that in the back of my head that might happen at some point. All right, so how do I set up this limit here?
X minus 5 to the n plus 1 over n plus 1 squared
Cool, just throw an n plus 1 wherever there's an n.
times 4n squared.
So again, I lose n of these, and the limit of this
1.
is 1. So this will be the limit and go to infinity of
X minus
x minus 5.
less than
Solve it for x.
Yep, solve it for x.
X minus
So we negative 1 less than this, less than 1, so I get x between
4.
4 and 6. That's 1 away from 5, which matches with the idea of the absolute value being distance. And then I just have to check the endpoints. I like it. So see what I mean? This is like a rhythm. I almost feel like a music teacher. There's a rhythm to this. You do this, and then you do this, and then you do this. So to check the endpoints. Oh, let's see. So if I let x be 4, I get the sum n equals 0. What happens if I let x?
Minus 1.
Yeah, this will be negative 1 to the n over n squared. Well, 1 over n squared already. So this absolutely converges. So it's awesome. It's going to converge. So what do I want to do with 4? Good. I want to include it. If x is 6, I get 1 over n squared, which of course, again, we kind of knew from the beginning that might happen. So I want to include that too. This converges too. So it's going to converge 4 to 6 inclusive. So put anything outside of that range, it's going to go crazy. Cool. So the one last quick little thing. You know me. It's just the way it is. I kind of alluded to this earlier, and I want to show it to you real quick. So remind me again, if I have a geometric series that converges, what would its sum look like? You got all the right letters in the wrong, yeah. So the sum will be A over 1 minus R, right? So now watch this. This is interesting. Now watch, you ready? So if I had 1 over 1 minus X, I can see that as the sum of an infinite series where R was X. So what do I know in the background's got to be true about X then?
It's got to be less than 1.
Less than 1. So I already know that going into this. This is backwards from what we're used to. So this is the result. Somebody got this. So they must have had an R that was equal to X. Because that's what they put there. And the first term was 1. So now think about that. R is the thing that I keep doing what with? Multiplying. That's one reason why it's called R, because it's a common ratio between one term and the one before it. And it starts at 1. So what would this thing look like then? Starts at 1.
1 with 1 times x.
1 times x.
1 times x squared.
X times x. X squared times x, right? Because I just keep multiplying by what R is. So here's an example of what I was talking about. And this is actually, this one kind of makes itself. But we're going to do this with any function. We're going to create this. And it's not going to be that easy. But this is one that's already ready-made for me. This is weird. As long as the absolute value of x is less than 1, then this is equal to that.
Now why do you
So-
have to put the absolute values on?
Oh, here?
Yeah.
Well, we know if we did the test, the ratio test, it would have absolute values on it. But also because that's just what the geometric R has to do. We know that's got to be between -1 and 1. Okay. So now watch. Somebody help me out. If I let x equal 0.1, just go with me for a second. Then this side would be 1 plus 0.1 plus 0.1 squared plus 0.1 cubed. Let's stop there. So what do you get? You get 1.111. You guys see that? 0.1 squared is just 0.01. 0.1 cubed is 0.001. So forth. So it just keeps filling itself in. Now what do you get on this side? 1 over 1 minus 0.1. Multiply by 10, you get 10 over 10 minus 1. 10 ninths, and what is 10 divided by 9? 1.111 forever. So I just want to show you a concrete example. We know this is true. If x is less than 1, this absolute value of x is less than 1. We know this is true just because it's geometric. So, but look at it a different way now. This function can be expressed using this infinite polynomial expression. They have the same value if you go to infinity. Would you go to infinity? No. The beautiful thing is you can stop somewhere. You can get as close as you want to. So if you don't need to be that close, I can stop here. If you need to be closer, I can stop down there somewhere. Now this is not a great example. This is where I got to start because it's one of the simplest ones you can see. But that function is not difficult. Right? If I'm you, I'm like, why the hell would I do that when I can just plug a freaking point in like we did? I agree with you. So when I have a really difficult function, I want to learn, can I make it look like this? Because polynomials are always easier than most other functions, right? So that eventually we're going to learn Taylor series, which is where I take any function and I can write it as a power series. And then I can stop somewhere and have an estimating polynomial for that function that works within a certain range, right? So you got to be always careful about that. That's plenty. Whew.